equilibrium lattice constant. As we have derived the L-J potential equation in our previous lecture, which is equal to UR for E sigma divided by R to the power 12 minus sigma divided by R to the power 6. As we know that this term is due to the van der Waals interaction, this term is due to the repulsive interaction, sigma and R are the length scale, and this gives us the potential depth. This is also shown by mu naught in many calculations. This equation is for the pair potential where we consider only a pair of atoms. Now if we want to generalize this equation to the whole crystal, then we have to consider the contribution from all n atoms. So the total potential equation will be equal to n by 2 for E summation over j sigma divided by Pij into R to the power 12 minus summation j sigma divided by Pij into R to the power 6. This is equation 1. We have ignored the kinetic energy interaction just for the sake of simplicity and for the ease of calculation. Here n is the total number of atoms. Half is used to avoid counting twice a single pair of atoms. This equation can also be written as half summation from I is equal to 1 up to n summation over j Rij. This is equation 2. Here this term is for the number of atom, total number of atom, and this is the Lj potential term. The first term is the sum for all atoms in the crystal, while the second summation is Lj potential term when I is the reference atom and j are all nearest neighbors. In equation 1, we introduce a new term, that is Pij, a dimensionless factor that gives us scale distance between the atoms. This is pure number. That is Pij R is equal to Rij. This is the distance between any reference atom I and the nearest neighbor j. This term is purely depends on the crystal geometry. Let us calculate the Pij R for the FCC crystal structure. As we know that the nearest neighbors in FCC is 12, consider the atom as a reference at having coordinates 0, 0, 0, while the nearest neighbor to this is at a by 2 and 0. This distance is equal to a divided by 2 under the root. So Pij r is equal to Rij is a by 2 divided by r. So Pij r is equal to Rij. The Rij value is a divided by square root 2 into r. Here a for the FCC structure is root 2 into r. So Pij turns out to be 1. For the second nearest neighbor, that is Rij is r2 for the FCC structure. The second nearest neighbors are 6 atoms, and the distance and they are a distance a apart. The second nearest neighbor in FCC is at a distance a, so Pij is a divided by r. Putting the value for the FCC structure is square root 2 into r, so it turns out to be 2, which is equal to 1.14. Similarly, for the third nearest neighbor Pij, r is equal to r3. The third nearest neighbor for the FCC is at a distance of 3 divided by 2 square root into a, and we have the third nearest number of atoms are 24. So Pij for the third nearest neighbor turns out to be 3 square root. Now using equation 1, which is equal to U total potential, using equation 1, which is equal to 2NE summation over j sigma Pij into r to the power 12 minus summation over j sigma Pij r to the power 6. Let An is defined as summation over j Pij to the power minus n, where for n is equal to 12 and 6. Thus An is sum over j Pij to the power minus n is equal to summation over all the shell zk pk minus n, where zk is the multiplicity which is the number of nearest neighbors and pk will be the value of Pij for that particular numbers. Numbers mean nearest numbers. Let this is equation 3. Thus equation 3 can be written as 2Ne A12 sigma to the divide by r to the power 12 minus a6 sigma to the power divided by r to the power 6. This is equation 4. We have replaced 1 over pij or pij to the power minus n by an. And this is for a12 and this is for a6. This term is, let us simplify, this zk is nearest neighbors, this is that scaling factor, that pure number we derived for the first nearest neighbor of the FCC, for the second nearest neighbor of FCC, and for the third nearest neighbor of FCC. So for first shell means first nearest neighbor, we have 12 nearest neighbor. For the first nearest neighbor, we have 12 nearest neighbor multiplied by the one scaling factor to the power minus 12. This is nearly equal to 12. For the second nearest neighbor, number of atoms are 6. The multiplicity is 2 square root minus to the power 12, that is nearly equal to 0.75. For the third nearest neighbor, we have 24 number of atoms. The scaling factor is 3 power minus 12. This is nearly equal to 0.002. For higher shell, or more further distant atom, contribution become more smaller. Summing to converge over R shell, this A12 is equal to Pij minus 12 is equal to 12.1318, and A6 Pij minus 6 is 14.4539. This means the nearest neighbor contribution contribute most of the interactive energy to the crystal. For equilibrium, let d by dr of U total at R is equal to R naught is 0. To find the equilibrium distance, get ut is 2ne, A12 is 12.1318 sigma r minus 12 minus A6 is 14.4539 sigma r minus 6, A and d by dr to 0. So this will be 2 minus e 12 derivative 12.1318 sigma 12 and r will be 13 to the power 13 minus 6 14.4539 sigma to the power 6 divided by r to the power 7. Here sigma 12, this sigma 6. This is equal to 0. Further simplification, this 12.13 sigma 12 divided by r13 minus 6 14.45 sigma to the power 6 divided by r to the power 7 equal to 0. After a few steps, we get r by sigma to the power 6 equal to 1.679. R by sigma is 1.679 to the power 1 over 6. R naught by sigma (1.09). This is for the many body system, as we have considered the interaction from all the n number of atoms. For the pair potential, this r naught by sigma is 2 to the power 1 over 6, which is nearly equal to 1.122. These are the most stable distances. This value is the same for all crystal having FCC structure. We can also write this is R naught sigma 1.09, where this sigma is the diameter of the where sigma is the diameter of the atom. Similarly, the cohesive energy at R naught is minus 215 into 4 in E. This can be obtained by putting R0 by sigma and Pij minus 12 value in the potential equation. Means in equation number 4.